So the first thing to confess was that I was told not to do a review. Let's see if I can get full screen here. In fact, it's a very good question of why was I asked to say anything at all. Well, I learned the answer the other day, which was thanks to Luis and Tepe's cartoon. I am the donkey, and I am here to tell you something from the donkey's perspective. But I think I really know why I'm here. It's because this is all my fault. 20 months ago, I sent a following email to Hero saying, anyone interested in trying to convince INT to organize a workshop on neutrino interaction modeling? I'm not keen to do it myself, emphasis added, but it might be a good idea and maybe something they'd go for. Maybe people like Sam Zeller could get involved. So, Hero, Sam, Jorge, Chris, everyone, I'm very, very sorry. I have not lifted a finger to do anything. I did not even make it. This is my payback, I think, being asked to speak on a topic in which I am probably unqualified. In fact, the graphic was perfect. This is me. And I've been trying to learn what I can as I watch the nuclear theorists and the experimentalists who really understand and deal with the cross-section issues come to grips with this material, because I'm a user. I promise I could quit any time, but I'm the end consumer of these cross-sections for oscillation physics. I came to this from a much happier land of low-energy solar neutrinos on the SNO experiment, where our experiences with nuclear theory were somewhat different, but I hope will give us nice parallels. When the SNO experiment was proposed, the deuteron neutrino cross-section at those energies, the claim from the theoreticians was this was calculable to 10%, and the experimental data was somewhere between 10 to 40%. By the time we actually got around to publishing any results, which was a decade or more later, the theorists were now telling us, oh, we've made a lot of progress. We can do this to 3% now, and we were extremely happy about that. As the experiment progressed, by the time we got to the end, the theorists were telling us, oh, we can now calculate this down to just over 1%, and better yet, the CC to NC ratio, which is what SNO cared most about, we can do that to 0.5%. At this point, we were not merely happy, but we were actually kind of frightened. And we were like, really? Are you sure? And that's what they would insist, that this was now understood. And so a lot of work went on in the theory side because SNO was an experiment that people thought warranted the effort. These next generation neutrino oscillation experiments are going to need to have comparable kinds of improvement in the state of the theory calculations. And obviously, it's going to be much harder than working at the MEV scale.
So here you can do effective field theory and do perturbation theory and
I know.
You're sure how small are you? Or
yes, I know.
You estimate very well next to leading order contributions and so on. Here life is different.
It's a different story. That being said, you know, coming as someone who's by no means expert in any of this, I'm certainly very impressed by all the different approaches we've seen and the effort that has already gone in from the nuclear theory community into these calculations. And certainly, we will plead guilty as experimentalists that we have not fully used this. And we are certainly using decades old models, and we beg your forgiveness and your patience. We are trying to do better, we promise. And we are especially thankful for those who have given us very practical advice on how you put some of these newer innovations into our generators. And maybe more will be said tomorrow in the generator discussions on this. But I want to echo something that Hugh said earlier today. And I will refer to Confucius. And Confucius had this very interesting theory that if you did not get your terminology right, you would not have social harmony. And I think we saw that in the last week as, again and again, people were talking past each other and certainly confusing the rest of us by using the same terms to refer to very different things. I mean, certainly the discussion of what is a spectral function was enlightening. Well, what's the opposite of enlightening? Muddying. Many of us found up feeling more confused afterwards because we thought we understood and now we don't. And then we'd go out in the hallway and someone would say, oh, what he was calling short range correlations. That's actually long range correlations, and we can scratch our heads a bit more. And I don't even want to think about what final state interactions means to, depending on who's talking about it. But what I want to emphasize is that one of the things that really struck me is that as a user of cross-sections, what I care about most often is a cross-section ratio. I am either using a near detector to predict a ratio or predict a distribution with a far detector, or in the case of mini-boon, I'm using, for example, mu-mu distributions to predict a nu-e signal. And we do this for a reason. It reduces our sensitivity to the cross-section systematics, and it makes it easier for the theorist to calculate something. For example, for T decay, we would desperately want to see what we can do by measuring rates in our near detector, which is carbon, to predict rates on its super K on oxygen. And similarly, we are often using nu-mu measurements to predict nu-e rates. And it was sort of shocking to me because I look at it and say, this is what we need, that hardly anyone was presenting calculations of these terms. Here's a paper I would like someone to write. Predictions of the ratios of the double differential cross sections for CC. I don't know, I can't call it Q anymore. I don't know what to call it, so I call it CC1P, 1H, 2P, 2H, resident pion, and DIS for carbon to oxygen. For neutrinos and antineutrinos in a relevant energy range. If you write this, you will be cited in every T decay publication from here until the end of time. We desperately need this kind of information. We have to believe that whatever disagreements or uncertainties there are in the models, or whatever limitations there are in the models, that many of those limitations, from a theoretical standpoint, we would have some naive expectation. They ought to cancel in a cross-section ratio. Just as in our experimental side, we are canceling systematics by doing a near to far extrapolation. Most of us have on the experimental side, have no clear idea for almost any of these, not even in the inclusive channels, of how well the models predict these ratios and how much accuracy the people building those models would claim on those predictions. With this, if this paper existed today, we could probably half overnight the T decay cross-section uncertainties. It comes into some technical details of how we use our near detector constraints. And I have to believe that this is a lot easier to calculate than many of the things that people have been calculating. So we would love to see this. Ulrich is not here, but these next slides are for him. There is one kind of consistency which concerns us primarily, and that is consistency with data. I'm going to be unapologetic. We are always, as experimentalists, going to be mixing and matching different models based with different assumptions, maybe even fundamentally inconsistent assumptions. But provided that we find that it predicts the data distributions that we need to do the oscillation analysis, we're going to do that, and we're not going to apologize for it. So let me say just a little bit, for example, about the Frankenstein's quasi-elastic model that T decay is trying to use right now. And we've heard a little about this, and maybe we'll hear more in the generator discussion. We have had years of using the relativistic Fermi gas and being taken to task, rightly so, for doing that. And people have been begging us, you need to use a spectral function. This has sunk through. We have put a lot of effort into putting spectral functions into our generators. One thing that I did learn this week is generally, right now we only do put spectral functions in the case where someone has explicitly given us a spectral function. If we don't have that, we throw up our hands and we run a relativistic Fermi gas for that nucleus. But I certainly had a very strong impression that it should not be that hard, and maybe some people have already done it, to give relatively simple scalings between nuclei. And we could certainly use some help getting, putting this into our generators. I also learned last week that spectral functions are wrong, they're obsolete, they're passé. We should never spend our time doing it, and 2 years have been wasted. But we've done it, and we're going to use it. So, on top of that, we're trying to graft on the second part of the Frankenstein monster, which is pick your favorite 2P2H model. And certainly, we've got a lot of emphasis in TDK, at least, on the Martini and Nieves models because they were available and most easy for us to try to put in. But of course, we're not limited to that. I got a little scared last week when Bill kept talking about how non-relativistic calculations should not be trusted. And maybe I'll ask Marco, these boost factors, how big a problem do you think this is? Do we have any way of knowing?
Yeah. For the moment, I don't know the answer. It is not a major effect on particle.
Okay.
I show some comparison on the transfer response in electron scattering, which appear in the paper of the Tracher and collaborator.
Mm-hmm.
The difference between Fourier relativity for something Mascarino, but the difference between a totally non-relativistic result, like the one of Alberico and so on, the Fourier relativistic is not so good. Just in the two-particle sector,
Mm-hmm.
the one particle only. Taking into account also in our
I hate that Juan is not here to defend his own work, but for the sake of clarity, I should say that to the best of my understanding, his two-particle to whole model is relativistic.
Is it completely?
In spite of what Bill said here.
there are some parts which are not relativistic, like the non-pi decay of the day.
Okay.
The parametrization of the delta equation, this is
not
the
relativist.
state or the non-relativist, but all the kinematics of the many-body diagrams, it's all relativistic.
Yeah.
Juan will be coming, right?
Yes.
So we can discuss this with him in person. Thanks. So we understand we cannot use the mech models and the spectral function at the same time. So I mean, what we are doing really is Frankenstein. We are using a spectral function for what I'm calling normal QE, for lack of a better word, 1P, 1H, whatever you want to call it. Let me rectify my terminology if I only knew how. We're doing something fundamentally different for this contribution, grafting onto it the best hadron model we have, which is what do you do for the momenta, turning off the pi-endless delta decay, and hoping that we haven't broken anything. This is the best we know how to do right now from the generator standpoint.
Add that we can do obviously a million cross-checks to show how bad our assumptions are in doing this, right?
Well, sort of.
Presumably that'll be something that feeds into the systematic.
Well, this is what I call, Frankenstein's always believed that it's okay to build a monster because you'd be able to control the monster. So maybe I won't go through it, but I'll make, Kendall's making this point that there are many checks that can be done on this kind of model. It's a terrible, internally inconsistent model, but we can at least get some idea of how it's comparing to what everyone else is calculating or what data we have. So these are just a list of some of the checks. I also want to point out something I'm not sure that people on the nuclear theory side have a good appreciation of. As an experimentalist, we are deeply suspicious of anything with a nuclear effect. As soon as you say the word nuclear effect, the first thing I think of is, well, what did I ever learn about a shell model and a magic nucleus and everything else, doubling magic, whatever. I go through all the nuclear physics I never really learned properly to begin with. I have absolutely no sense of which differences between nuclei matter, which ones do not. And in my view, any nucleus is guilty until you prove to me that it's innocent. So my nightmare is I could build the world's perfect detector. I could go maybe do a high-pressure gaseous TPC and measure interactions on helium or neon or something small that you think you can calculate from the theory side. And you might be able to have a theory that predicts all of it. But how would you convince me that it all can be used to understand a much heavier nucleus? I mean, let's not even think of argon. Let's think of oxygen. I think this is something I would like to hear more about. Maybe it's just obvious to the theory community which features matter and how robust scalings are between them. This goes back to this question of cross-section ratios, but it's completely not obvious to those of us who aren't expert in this. And I think Hugh made this point maybe better than I will. we have to use hadronic information in our analyses, even if you don't like it and even if you say you can't calculate it. But the incentive is that I would rather a competent theorist make their best guess and where they admit that they are guessing, because if they don't, I'm going to make my best guess, and you don't want that. I think if someone working on the theory side, you should always be asking yourself, an experimentalist to use my model, and I hope that you want us to use your models or else you wouldn't put in the effort, is always going to start out by saying, I need to put actual momenta on every particle coming out in the final state, or else we can't use it for our data analysis. However crude it has to be, you have to give us something. We'll have some discussion tomorrow about how we might make it easier to get these models into our generators, and maybe we shouldn't go into that today.
I think one point there is that it's possible that one theory or one framework isn't able to, you can only do one part left-hand side, and someone else has handled the hadronic side, and it would be great if you could form an appropriate partnership to get both of those things together.
Yeah, I mean, effectively, this is what we're doing on 2P2H right now. Jan has grafted on something on top of the leptonic side that others have done. And we have to do that. The other thing that I want to point out is that there is something missing so far from all these discussions. And don't get me wrong. This is I believe this is yours, right, Marco? I mean, this is a beautiful work. We love it. We want to use it. And we're grateful to have it. But what we actually would hope to get is this, which is an uncertainty on the theory side. And again, this is a case where if we're not given this, we will make it up. And the reason we make it up is fundamentally because of how we use these cross-sections. What we are always measuring is a convolution of a flux and a cross-section. This is data from T to K, where what we are doing is we are doing a simultaneous fit of the data distribution, in this case muon momentum, to the flux and the cross-section, where we have assigned uncertainties to each of these, and we are allowing the fit to drive this to the best values. If we do not have an uncertainty on the cross-section, what happens in the fit is all of the variations between data and Monte Carlo get driven into the flux parameters. And that certainly is going to mess up our near to far extrapolation. So we are always, and I mean almost always, putting in some kind of uncertainty model on how the cross-section parameters could vary. And these are these famous nuisance parameters. They don't refer to people, in spite of what you may have thought, but they refer to the fact that we need to have some knobs in the models that allow us to vary the cross-section predictions. M sub A is the most infamous example of this. But if we don't have physically plausible models or knobs that we can turn, we put in physically implausible ones, because we don't really have any option. If we don't have some way of varying the cross-section predictions to account for data Monte Carlo discrepancies, we can't use it.
They don't always refer to people.
Yeah, sometimes they could. So we really, really need some kind of even ballpark range. Now, to a certain extent, we're not super sensitive to what the exact uncertainty is on the theory side. We do use our near detectors to constrain this as much as we can. One thing, though, I think we have to be very careful about is whether the model prediction was itself tuned to data. Or even if you provide an uncertainty on your model prediction, is the uncertainty due to a data study? For example, what we almost always do is we take whatever model we're looking at, we then try to fit it to all the world's cross-section data that we can get to see how well it works and to sort of get an idea of how far off the theory could be from the data. And maybe, obviously, if you've already tuned to that data, the agreement is going to look very good, but not because the model's so good, it's because it was forced to be that good, right? And even if you didn't tune, even all you did was take the data to Monte Carlo difference and call that your uncertainty. Well, if we then do another fit, we're effectively double weighting whatever experimental data went into that. And so once again, we wind up, in that case, underestimating the uncertainty there. I think one of the things that really struck me, particularly when listening to the electron scattering talks, is a point that I'd always taken for granted. It has always been obvious to me that, of course, you don't know the energy of the neutrino. That's what we're trying to measure, right? I just want to close with sort of an idea that's been kicking around. This is certainly not my idea. In fact, it is much more Kevin and Mark and Mike Wilking, who's not here. But the idea is as follows. We are using these off-axis beams now, where we go off-axis because the flux varies with the off-axis angle in a predictable way. And for example, this is TDK's Ingrid detector, which actually measures these variations, mostly not for cross-sections, although we do some cross-section measurements, but in this case, just to get the beam pointing right. And one thing that was pointed out, and this is a slide that Mike Wilking at TRIUMF made, and I'm just stealing here, is that if you look at how you vary with off-axis angles, and you imagine having a detector where you were sampling as the kinematic distributions, just say even the mu on the left-hand side, as a function of off-axis angle, because the energy is shifting with the angle, if you do a nice trick of, for example, taking the 3.5 degree bin minus the 2.5 degree bin plus some weighting of the 1.5 degree bin, you can produce, with appropriate weightings, at least in a high statistics limit, very narrow, not really monoenergetic, but much closer to monoenergetic neutrino energy distributions than what the beam actually gives you. Effectively, you're using the fact that you know how the energy spectrum varies as a function of off-axis angle to sort of deconvolve what the actual energy distribution is. And it's a little hard to see. Maybe you can't read this, but this is, for example, a 1 GeV bin. Here's 0.8, here's 1.2. So, I mean, that is a 10% and very Gaussian looking thing. So imagine that you did an experiment where you had a series of detectors, or at least a detector that you regularly moved and scanned across off-axis angles. If you collect enough statistics, you may be able to, in a much more model-independent way, extract how the initial neutrino energy relates to the lepton kinematics. And this is really the only way I know to minimize your sensitivity to all the hadronic garbage going on. But everyone says, we just want to, can't you just get by with the lepton only? The only way I know to do it is this. I mean, maybe people have other clever ideas. Certainly, this is not my idea in any way, shape, or form, but I thought it would be an interesting thing to just mention here. I will also point out that we need to think ahead as to what our signals and backgrounds really are. We spent all last week talking about how QE reactions, or 0 pi reactions more exactly, were so critical for the oscillation measurements at, for example, T to K. Obviously, NOVA and LB&E and experiments at higher energy have to worry about other interactions. But even at T to K, this is we now have got a much better reconstruction that can quite effectively find charged pions in the final state. I will be shocked if in the next 2 years T to K is not regularly including CC1 pi events as part of their oscillation analysis and trying to reconstruct the energy of those events using the delta hypothesis as opposed to the QE hypothesis. And so we're no longer, there are a lot of statistics there. We want to use it. And lastly, just to be very pessimistic, I'll just repeat something I made as a brief comment earlier. Nu-E is very, very hard because we measure everything in beams with nu-mu. And certainly Kevin can tell you much more about the issues with this than I can. If you're really going to get 2% measurements for a delta CP measurement, you're going to have to really improve this from a theory standpoint, or you have to build a beam that has an appreciable nu-E flux that you understand. So that was everything I had to say. If there's no questions, we can go to Jan.
Yeah, that's the one question. Is the new cross-section extrapolation So those errors should include something about